Back in 2020, a paper landed that completely changed the game in artificial intelligence. It was called Scaling Laws for Neural Language Models. And look, it wasn't just another research paper. It was basically a map that showed everyone the predictable path to building the massive AI models that we are all talking about today. So let's dive in and see how this one paper really did change everything. I mean, really think about that question. What if it was that predictable? Before this paper came out, making AI better felt like, well, it was part science, part art, and honestly, a whole lot of luck. But this paper came along and suggested something totally radical, that the secret to more powerful AI wasn't about finding some clever new design, but about something way, way more predictable. And this slide just nails the shift perfectly. The whole field went from being this kind of alchemy, where researchers were constantly tweaking all these little complex knobs just hoping for a breakthrough. And it turned into a straight-up engineering discipline. The answer to the question, how do we make our model better, suddenly became almost shockingly simple. Just scale it up. More parameters, more data, and more compute. So to really get how big of a deal this was, we're going to walk through 5 key parts. First, we'll look at what the world was like before these laws. Then, how the paper brought a sense of order to all that chaos. Third, we'll get into the 3 specific laws themselves. Fourth, and this is a big one, the surprisingly simple recipe for the best way to train these things. And finally, the incredible legacy of this work. Okay, so let's just set the scene. Before this paper, the AI research world was, well, you could call it a pre-scaling fog. People were definitely making progress, but the path forward, it was anything but clear. You have to understand, making progress was a real grind. Researchers were publishing papers on all these little architectural tweaks, changing the depth of the network, the width, the number of attention heads. It was a world of endless hyperparameter tuning, which is just a fancy way of saying fiddling with dozens of complicated settings to find some kind of magic combination. As the paper itself points out, performance just didn't seem to care that much about the model's exact shape. There was no big unifying rule that said, hey, if you just do this, your model will get predictably better. And then right into the middle of this fog, this paper arrives like a bolt of lightning. It gave everyone this moment of just profound clarity. It basically said that underneath all that messy complexity, there was a simple, beautiful order. This quote right here from the paper's abstract, "This is the heart of the revolution." What the author showed was that a model's performance, or more specifically, its error rate, its loss, it wasn't random at all. It followed a predictable mathematical curve, a power law when you scaled up 3 key things. And these weren't just small trends. They held true across 7 orders of magnitude. That is a mind-bogglingly huge range. So what even is a scaling law? Well, the easiest way to think about it is like a law of physics. It's a formula that tells you exactly how one thing changes when you change something else. In this case, it says that as you make the key ingredients bigger, the model's error rate gets smaller along a smooth, predictable curve. For the very first time, building better AI had a recipe. Okay, so what are these magic ingredients? Well, the paper zeroed in on 3 fundamental factors that really govern how well a language model performs. The first one is N, which stands for the size of the model. The second is D, for the size of the dataset. That's all the text the model learns from. And the third one is C, for the raw compute or computational power you throw at it. Now, for model size, the paper found a really crucial detail. These scaling laws worked best when you only counted the thinking parts of the model, the non-embedding parameters, not the parts that just store vocabulary. That little insight is what made the relationship so incredibly clean and predictable. And here are the laws themselves. Now, you don't need to be a math whiz to get the big picture here. For each of these variables, N, D, and C, the loss, which is L, is proportional to 1 over that variable. In plain English, that just means when one thing goes up, the other thing goes down, predictably. This was huge because it meant you could actually forecast how much better your next model would be if you, say, doubled its size. But the paper did more than just point out the laws. It gave us the recipe. And this next part is maybe the most practical and, at the time, the most counterintuitive finding in the entire study: how to best spend your limited compute budget. This quote just completely turned the conventional wisdom of the time on its head. See, the prevailing idea was that you should train your models until they just stopped getting better, train them to convergence. This paper came along and said, nope, that's a total waste of compute. The most efficient path to a better model was to build a ridiculously huge one, but then train it for a surprisingly short amount of time. And this chart just visualizes that insight perfectly. It answers a simple question. If somebody gives you a massive increase in compute power, how should you spend it? The paper's math shows that you should pour about 73% of that new budget into making the model bigger, about 24% into processing more data at once, and a tiny, almost insignificant 3% into training it for longer. The takeaway was crystal clear. Make the model bigger, above all else. So that brings us to the legacy of these laws. Because the impact here wasn't just academic. It sent shockwaves through the entire industry and led directly to the AI boom that we are all living through right this second. You can literally see the effect on this timeline. The paper gets published in 2020, and that very same year, OpenAI, where the authors worked, releases GPT-3, a 175 billion parameter model that just blew everyone's minds. It was the scaling laws made real. And then came Google's PaLM, and after that, GPT-4. Each one a massive leap in scale, all of them built on the confidence that these laws provided. At the end of the day, what the scaling laws really did was give big companies the confidence to make multi-billion-dollar bets on AI. You have to remember, building these models takes gigantic data centers and years of work. Before this paper, making that kind of investment was a huge gamble. After this paper, it became a predictable engineering investment. You knew if you spent the money and the resources, you were going to get a better model. And that leaves us with a really fascinating and honestly a slightly unnerving question for the future. We have seen such incredible progress just by making things bigger. But what happens when we can't do that anymore? What happens when we've trained on every piece of high-quality text on the internet, or when we just physically can't build bigger data centers? The scaling laws gave us the map for the last incredible chapter of AI. But the map for what comes next? Well, that's still completely unwritten. This is for entertainment purposes only.